This is a video for MEI Core Pure Mathematics, Vectors 3, Equations of Lines, 3.4, the intersection of lines in 2 dimensions. In 2 dimensions, there are only 3 things that can happen. The 2 lines could intersect at one point. So here you can see there's a single point of intersection. They could be parallel and not intersect, and in 2 dimensions these 2 lines will never intersect. Or they could be parallel and collinear, and although these are lying very closely side by side, it's intended to show that actually they share a point and a direction. And we've already looked at that in a previous video about how to decide whether or not 2 vector equations of lines represent the same line. So let's have a look at an example. Let's try and find a point that lies on both of these lines. Now, we know that it will be one of those 3 situations. Either there is a point of intersection, or there is no point of intersection, or they will actually intersect everywhere because they are the same line. So I'm just going to call these lines L1 and L2, and although they've been given in IJ form here, it's actually easier to see what's going on if we write them as column vectors. So if I look at the x components first of all, that's these 2. They must be equal if they've got a shared point. So 5 plus 2t is equal to 2 minus s. And notice that these 2 equations use different parameters so that I don't get confused about the parameters, that t and s may well have different values. The other thing I've got from the y component is I've got 11 plus 6t is equal to 4 minus 5s. So if I take this first equation and multiply it by 3, I'm going to get 15 plus 6t is equal to 6 minus 3s, and I've got the other equation 11 plus 6t is equal to 4 minus 5s. If I take these 2 away now, I'm going to get 4 from the left hand side, and I'm going to get 2 plus 2s from the right hand side. And this gives me s equals 1. And if s equals 1, we can work out what t is. Well, this is going to tell me that 5 plus 2t is equal to 1, and that gives me t is equal to minus 2. So I've got s is 1, t is minus 2, and pick an equation. It doesn't matter which one you pick. Let's pick t equals minus 2 and plug it into L1. So that would suggest that 5 plus 2 lots of minus 2 and 11 plus 6 lots of minus 2 will give me my point of intersection, and I get 1 and I get minus 1. So they intersect at 1 minus 1. Now from here I can see that my direction vector is 2, 6, or even 1, 3 if you divide it down. Those are parallel. And my direction vector here is minus 1, minus 5, which we could think about as just being 5 if I strip the minuses out. And we can see that these 2 are not parallel, so they do intersect. So I know that I'm going to get a single solution. If these were parallel and had no result, then from here, from this type of working out, I would end up with something which was inconsistent, typically 1 equals 2 or something. And if they were collinear, then from here I would end up with something which is consistent, and typically something like 0 equals 0. In other words, that it would be satisfied everywhere. There's that working just written up a bit more neatly. Here's the pair of simultaneous equations, and we've seen the working for that to give us t equals minus 2 and s equals 1. This piece of working has actually used s equals 1 into the second equation, and we end up with the same result, 1 minus 1. And as we've said here, you could check that using t equals minus 2, which is what we did on the previous slide. The next and final video in this sequence is 3.5, the intersection of lines in 3 dimensions.